Thanks for the introduction. Good morning, everybody. Thanks for coming to this talk. And today, I have the privilege to present our work from Oak Ridge National Laboratory on an algorithm on how to process in a very efficient way point cloud data to generate as-built dimensions for building retrofits. I would like to acknowledge my co-authors, Nolan and Diana Hon from Oak Ridge National Laboratory, and the support from the Department of Energy through our program manager, Sven Mumen. So, all right. So what is the motivation for this work? Well, in the US, 50% of the buildings were constructed before energy codes. So how can we enhance the thermal efficiency of these non-compliant buildings? And as we heard in many talks yesterday, using prefab components, because these are high-tech panels that present a lot of thermal advantages for the building envelope. So one way to do it is through demolition and rebuild. This generates a lot of occupancy disruption. It takes long preparation and execution times, and it could incur in high costs depending on the conditions of the building. Moreover, this practice is not fast. So a recent survey in the US presented these results that less than 2% of these buildings are retrofitted each year. So for the climate goals that the US government wants to achieve, this is not fast enough. So we need to accelerate the retrofit of these old buildings. So one option is the overclad envelope retrofit solution, in which what you do is you do not get rid of the old envelope, but rather you install these high-tech panels over the old envelope and then enhance the thermal properties. This generates a minimal occupancy disruption because you don't get rid of the occupants. They can be inside while the retrofit process occurs. It takes short construction time at the job site. As we saw also in many talks, there are many ways to efficiently assemble prefabricated panels. So there is potential for lower cost. And the main thing for this conference is that they present a potential for automation. But as one of the key speakers, Professor Maldonado, presented yesterday, accuracy is key. So suppose that you have this example, you want to retrofit this old building, and you design your panels for the retrofit process, but you have inaccurate as-built drawings. So you have errors. So for example, you use the as-designed drawings instead of the as-built dimensions. So there will be some incompatibility there. Then you go and do the retrofit, and whenever you're installing them, you realize that, for example, panels are overlapping, so you have to rework them and remove material, or you have some lack of material in some specs, generating air gaps, and then your thermal efficiency decreases. So how then you go from the building you want to retrofit and generate the as-built dimensions for the drawings and design of the panels? So right now, the business as usual case is that you send a person to the site to inspect and detect where the features of the building are, where the doors, where the windows are. Then you measure it, and it could be as rudimentary as tape measurements, or it could be through point clouds, but still there is manual segmentation of this point cloud. So there is some human measurement error here. After that, you have to when you get these dimensions, you have to perform the architectural design drawing, which also incurs some human error. And this cumulated error could be problematic at the job site when you're trying to assemble these panels. So what we're proposing is to automate and minimize the error here. So what we are proposing is to use a very accurate LiDAR point cloud data, and these are already available in many total stations. So here you're only dependent on the resolution of the instrument. Then you have an algorithm to automatically perform the segmentation, and extract the components of the building, of the envelope, windows, doors, and so on. And finally, once you use these automated dimensions, you can generate automatically a wireframe model that then you can export to AutoCAD and do your optimal panel design. But the main thing of this is that there is no human error involved, and what you're relying is on the resolution of the instrument. So how to automate this? Well, very popular methods are machine learning methods, where they are adapted to handle a large amount of data. And right now, there are two main thrusts. One is using cameras, and the other one is using point clouds through LiDAR sensors. Or you can also use a sensor fusion and use both sensors to perform this. However, resolution is an important topic. The resolution of the camera is lower than the resolution of the point cloud. We're talking about 10 order of magnitude. This is because in the camera, you're constrained by the pixel size, okay? Even if you have a high resolution camera, suppose that you want to take a picture of a large envelope, you have to move the camera away from the envelope, increasing the size of the pixel relative to the features you want to capture. In point clouds, in modern total stations, you can achieve sub-millimeter resolution even at 1,000 meters away from the envelope. Now, on algorithms, the favorite algorithms for this, and algorithms that have been discussed also in sessions yesterday, are supervised algorithms or neural networks, okay? And there has been work done for all of these types of sensors and resolutions. However, if you look of the application for envelope retrofits, you see that the application is mainly for camera application. And this is because there are very well-refined algorithms to detect windows and doors through pictures. You can use sensor fusion, but because you're depending on the camera to do the segmentation, then you are relying on the resolution of the camera. On the point cloud, you have only point clouds trained on objects such as tables and chairs, and not really features of the envelope. So you have two issues here. Either you don't have enough resolution because you depend on cameras, or you have a lack of labeled training data because there is no library of point cloud trained of windows and doors. So what we are proposing here is an unsupervised method for pattern recognition. And that is what I'm going to talk about today. So AutoCubes stands for Automatic Point Cloud Building Envelope Segmentation. And what it does is it takes a point cloud data. There is some calibration from the user depending on the complexity of the building. And then it filters through a machine learning algorithm to generate an accurate wireframe model. This is the example I'm going to talk about. You have this building. This is a real building from Knoxville, Tennessee, that we're going to retrofit by the end of next year. And this consists of 32 million points. Then the algorithm processes it and generates a wireframe of around 300 points that then you can import into AutoCAD or similar software to design your panels. And this work attempts to move further and further towards the near real-time digital twin generation of building envelopes. So I'm going to discuss the main ideas. You can see the details in the paper. But the main ideas is how can you systematically extract features? So if you look at a plan view of the building envelope through the point cloud, you see these clusters, these dense clusters of points, 4 of them, in fact, because we have 4 walls in this building. If you look at each of these clusters, then you can extract each facade. From the facade, then you can do clustering to break the facade into sections, each section corresponding to a particular feature of the building, a wall, or sorry, a window or a door. This is important not only for cleaning up the point cloud, but also you will see that This is key for removing assumptions of considering a planar wall. Turns out that as-built walls are not necessarily flat. And with this method, you can capture the curvature of the walls, but you will see that later. This is the main assumption of the paper. How can you separate windows and doors from the wall points? This is the side view or of a typical facade in residential construction in the US. You can see that the exterior wall belongs to a plane, and the window is recessed with respect to the wall and belongs to a second plane. So again, if you analyze the density of points here, you see clearly a peak of density where the wall is, because this has the large number of points. And you can see, maybe you can see this little bump in the interior of the facade of the point cloud, sorry. This little bump corresponds to this window. So you can break the density into distinct parts. This is done automatically. And you can take this exterior wall and separate it from the interior points that have the window inside. Also, just to check our assumptions, you see that the exterior points correspond to the window sill and the eave of the facade. Now, from the interior point, another observation is that you can capture features of the roof, or maybe there are some leak points of the wall here, but there is a clear cluster that contains the features that we want. So we can use a very popular algorithm called a DB scan, which identifies the cluster that has the higher density of points. And once you extract this, then you can see how clearly we can capture where the windows are, where the doors are. Once you separate this, finally, you just collect all the points that belong to the wall. And then here, look at how this wall has a curvature. We're talking about millimeters, but still, for retrofit purposes, this is important. So the algorithm generates this heat map. And this is very important because this tells you the highs and lows of the curvature of the facade. And you can then use this to optimize the connections for your overclad retrofit panel. So the new envelope, the retrofit envelope, will be flat because you can take this into account and optimize the connections, taking account the curvature of the as-built facade. Finally, another assumptions here is that we're assuming that windows and doors are rectangular. So you can bound the doors and windows with the bounding boxes to get the dimensions and positions. And we're also assuming that the facade itself is convex, so we can extract the convex hull very efficiently. And then with this, you collect all of this information from all the 4 different facades, put them into a wireframe, and export it to AutoCAD for further development of the retrofit panels. Performance. Right now, with the example that we have, this algorithm can analyze 32 million points in less than 10 minutes. Most of the unsupervised machine learning routines have been optimized, except clearly for one. This is the density-based clustering. And this is just the nature of how the algorithm works, because it has to kind of like look around for points and look at neighborhoods. And this just takes time. But there could be ways to reduce the time of this chunk of processing here. But most importantly, I started this by talking about the accuracy, right? So this is the main point. This is the heart of the results. The dashed lines, this shows the error compared between the algorithm output and manual measurements done by my colleague Nolan. The dashed line shows the resolution of the LiDAR. In this case, we took this point cloud with a resolution of 3 millimeters. You can see how 3 of the facades present very good results within or close to the resolution of the device. One of the facades have clearly large errors, and this is to because of the way we collect the data. Knoxville turns out to be very hilly, and this particular facade was on a hill. So the LiDAR had to be, the LiDAR sensor had to be put on the top of the hill and collect data shooting down. So it's not ideal, you're not perpendicular, and you're not at a similar height. So this is something that we still need to analyze on the sensitivity of where you position the LiDAR sensor in order to minimize this error in the automation. But in any case, we could have, we had an average error of 4 millimeters with this resolution. So we're still very close to being asked, to obtaining errors closer to the resolution of the device. Conclusions of this work, unsupervised machine learning methods were used to overcome the scarcity of labeled examples of building envelopes. In fact, we are envisioning this as a method to build a library of building envelope components so we can train supervised machine learning methods that can be more efficient and near real-time execution. The algorithm right now can process over 32 million points in less than 10 minutes with a maximum absolute error of 4 millimeters, considering that we collected this data at 3 millimeter resolution. We have a beta version available if somebody wants to try it for academic or R&D purposes. And the main caveats, I show you a bunch of things that work, but the main caveat that it only works for single floor buildings with 4 perpendicular facades. The main assumption of the recessed window with respect to the wall. And right now, the wireframe that is exported corresponds to convex facade with rectangular features. And as I told you, this is being used to optimize the panel design of assemblies for buildings that will be retrofitted in Knoxville, Tennessee in 2024. So with that, thank you. I also added some information about another DOE initiative here in India and the Solar Decathlon, and I will welcome some questions. Thanks.
Thank you, Bryan.